very much, Anik. You summarized yesterday's training. And very good morning to all. Hope you are still very enthusiastic. And today we'll learn about the data missing values handling. So how we could handle the data missing values. And various methods we will introduce, and then later we will show you how we implement it in R. Yeah? But also very important is how we could identify the magnitude, the structure, and the distribution of the missingness in the data. That will also be included in our session. Yeah. Now let me start with the session 5.1. Sorry. Okay. Today, okay. Can you see on the screen?
Yes.
My presentation. Okay. Now the basic concepts. Yeah. Yeah, we see missing values almost every day, especially for you who are working on the data side, analysis, dissemination. And they can show up in terms of the NA, or the blank cells, or the none, or the 99 code, and many other things. But the important thing is that what is the magnitude of them? If it is very small, then maybe we can just leave it out. But if it is rather substantial, then we need to find a way of addressing this. Yeah? And in finding a ways of addressing this, we have to identify more or less the distribution. And before that, I would like to mention about the types of missingness, because we have to be aware of this. And not all kinds of missingness can be imputed, actually, yeah? Strictly speaking. And there are three kinds of missingness, depending on the underlying mechanism, yeah, that bring them to be missing. Number one is the M-car, missing completely at random. And then second one is MAR, missing at random. So we drop the completely. And then number three is missing not at random, or somebody call also non-missing at random. M-car, missing completely at random. Yeah, this is really completely at random. Yeah. So when it is at random, this means that the missingness is not related to the data. It's not related to any variables in the data. It just happened there randomly. Yeah? And this may be because of the bad luck. Yeah? The questionnaire cannot reach the respondent. Yeah? This is completely at random. And for example, again, the weighing scale in the survey, example, ran out batteries. So nobody knows when it happens. And then for this, because this is really completely at random, actually, strictly speaking, it's difficult to forecast. Yeah. So the best way for this, if the magnitude is, I mean, not big. Yeah. I mean, if the amount of the sample is not our major concern, then we can just delete the missing. And this deletion of the missing today will not affect the distribution. Why? Yeah, again, because they come there at random, so they spread anywhere we don't know. And the data is also random, so basically the distribution of the missing data and the observed data are not different significantly. So when you remove that and you use only the complete data, you will not run into an unbiased estimate. Yeah, so still you will not run into a biased estimate. Yeah, still unbiased. Your estimate is unbiased. The only problem is that because you reduce the sample, and then maybe the variance little bit higher. That's all. Okay, and the MAR missing at random. This is also random, but not completely at random. Yeah, so partially at random. So this means that this missingness, probability of missingness of the missing value, maybe most likely related to some variables. Yeah, some variables. So it applies only some groups. For example, related to the gender. Yeah? The gender-related missingness. Maybe male tends not to respond to questions on household expenditure. Could be. And then female not responding to the question on weight, on maybe on contraceptive, something like that. But if you ask the male, they will answer. But if you ask the female, maybe most of them will refuse. So this is the kind of missing at random, yeah, related to other variables in the survey. Maybe related to urban phenomena, and high income phenomena. The rich people, we cannot enter. Yeah, it's not because anything, not because they don't like the survey, but they just never open the house. Yeah, so there's a problem with that kind of things. So we can say that okay, if we then take into account the gender, that gender-related missingness, yeah, or we take into account this income, maybe we can improve our estimates, right? So we can refine our analysis. So that is the idea. That again, maybe the main difference is that in the MAR, missing at random, we still can rely on other variables to get the estimate of the true answer. Of course, we will not get the true answer, yeah? But just the best guess. And I should also mention that the mice, we'll talk about the mice algorithm. Mice is the multiple imputation by chain equations. This is the best algorithm. I will also illustrate to you. This assumes that the missingness is MAR. And actually, most of the missingness is actually can be considered as MAR. Yeah? Very little maybe due to the completely random. Yeah. And the other one is missing not at random. Not at random. Yeah, not random. This is intentionally, yeah. Maybe related to the anxiety. You ask people about politics. Those who don't have interest in society but politics, maybe they don't respond. But anxiety is not observed, right? It's not observed. So MNR depends on the unobserved variable, but also actually to some extent also to the observed variables. Yeah. But the MAR, the second one, this is related to the variables in the data set. So meaning this is related to the observed variables. I think that's all I would like to highlight. Yeah. Respondent burden may be related to the MNAR, missing not at random. Yeah, if the questioner is so sick, respondent become fatigue and the answering only some of the questions. This leads to the missingness. But this is not related to their age or their whether they live in urban or rural or whether they rich or poor. But this is related to unobserved variable. They are so burdensome, yeah, with the survey. And this kind of more or less can help you visualize the missingness mechanism behind the MAR, MNR, and the MCAR. Yeah. So summarizing this, the MCAR missingness is completely at random, not related to any other variables, and MAR is not only related to the observed, but maybe also to the not only related to the observed, while the NMAR related to both. Yeah, but mostly on the unobserved. This is just another way of explaining consequences I mentioned. And the MCAR actually is only related to the variance. Yeah, and the estimate is unbiased. But the MAR estimate can be unbiased if you impute it with proper method, can be unbiased. I mean, at least reduce the biasness, yeah, still reduce the biasness, and the variance still also can be not biased, can be unbiased also if you use the proper methods. The MNR, this is the most complicated actually. It depends on unobserved variables mostly, yeah. But because of this complicacy, in practice, normally experts treat the MNR the same as MAR. Yeah, so you can consider them as MAR. So we can also impute them, apply the methodology as in the case of MAR. But again, the MCR, the MCAR, is something that actually there is no method we can use except that we delete them, but hopefully it's not that big, yeah, the amount. So with that in mind, I hope it's not so confusing, yeah? Not so confusing, and we have some idea that okay, that our data maybe can be imputed because most of data actually missing at random, not missing completely at random, yeah. completely at random, we don't have any idea at all. Okay. Methods for handling this. So now we should think about the method for handling that one. You want to impute the MAR or MNAR, yeah, and there are a few methods. What's that? Complete case method. Complete case method is the one for the MCAR. MCAR, as I mentioned. MCAR, we can analyze it by deleting the messiness. So this is called the complete case method. We are only looking at the complete data. Yeah? So the messiness we take out. Normally, it is okay if less than 5%. If greater than 5%, maybe we should find ways of improving our data. Yeah, maybe using the educated guess, like that. And then on the imputation method, yeah, of course, this is mostly for total MAR, missing at random, and for the MNAR. Imputation method, depending on the nature of the data, some of the imputation methods may be appropriate, yeah. Even the simple one can be appropriate when the nature of data really allows for good estimate. Let's see one by one. We have this is for the longitudinal survey. That's very good. Longitudinal is the survey where the respondents are the same from this year to next year. Next year they are the same respondent. Yeah? Or if the survey is monthly, also the same monthly. So for this, we can use this method. Yeah. Last observation, carried forward. So meaning that if we don't have the figures for this year, we can use last year figures. Last year, or if the last observation is 2 years ago, you can use 2 years ago. So the last observation carried forward. So this normally still makes sense if the survey of the data is the type of longitudinal, yeah, longitudinal. And then in dealing with time series data, we will also see later how to handle missingness in time series data. Interpolation normally works. Yeah. And then there are the methods: mean imputation, median imputation, mode imputation, regression, then KNN, the K nearest neighborhood, KMM, multiple regression, multiple imputation, we'll see later. Mean, median, and mode. Mean imputation is clear, yeah. We fill up the missing data using the mean of the same variable. Okay. And this could be fine if the data does not show big fluctuation. If the data is stationary, especially, this is very good because the mean may not be so different with other observations. But if the data fluctuates a lot and you take the mean, but what is missing is actually something to do with the lower part of the sample, yeah? The poor sample. The poor we will impute based on the average. And then you can see the impact. Yeah? It's very, very overestimated. Or if we are inputting someone with very high income with the mean, this also doesn't make a good sense, right? But again, if the fluctuation is still okay, then maybe this is good. We can also use the median mode. Yeah, we'll see how it works in the R. I've mentioned this, some drawbacks. Would be realistic if data is particularly not fluctuating a lot. What is this? Oh yeah, the standard error. Standard error also affected, yeah. If you do the imputation using mean or median, then you underestimate the standard error, right? Because when the data is fluctuating, and then 10% or 20% will be missing, and you replace them with the mean. So you can imagine, and the standard error would be decreasing because there are so many values having the same value, right? No variety. And this is a bit serious if the data is fluctuating a lot. Regression imputation is history we learn about regression with so many caution. But of course, in this kind of imputation, we normally use you normally don't test the regression, don't test, and the algorithm will not possible to test the assumption, etc. Yeah? But the idea is that we have many observations. We are talking about univariate. Yeah, we're talking about only one variable. We see one column. There are some missing there. And actually, it is still a good guess if we develop this missing data using the regression. Yeah? We, based on the non-missing data, we estimate the regression, and then this is correlated to other variables. Yeah, of course, if income missing, then we have, for example, employment, and then we regress income to employment for the non-missing data, and then using the value of the employment related to the missing data, we predict the missing data. We can do that. Also, you do the trend, it's also possible. You do the trend just looking at the income, one variables. This still can make sense, yeah? Again, if the situation is not that worse, the data is not that worse. Actually, for not so big data, we can observe, right? We can observe, we can plot the data and see the likely that we can apply the regression. Yeah. Again, if the data behavior is not predictable, and then maybe it's not a good idea to use regression. But if the data is moving a bit smoothly, like talking about the unemployment rate, maybe they don't move a lot, yeah, maybe we can still use this. So again, depending on the data, the nature of data and the missingness, you can apply even the simple method like this. Of course, the problem with regression is that we somehow also underestimate the variance. Yeah? We know no data is moving very smoothly along the line. Yeah? they move up down around the line. Yeah? So if we estimate this with this straight line, then of course there are some effect on the variance. Yeah, the variance become a bit smaller than the usual. Okay, then but it should be. This is an example of the classical example, the bill and the tips. Yeah, from the retail sales restaurant, they're mostly highly correlated. So if we have missing value of the bill, we can use the tips, yeah, to build the regression model and estimate the bill. This kind of close relation is in place. Maybe the estimate is still acceptable, yeah. Okay. The nearest neighborhood. This is basically also based on the assumption that the value, the current value, the missing value, may not be far away from the neighborhood. But the concept of neighborhood, you can imagine this can be a mean, yeah, with the average of the observation on the right and on the left, or mode, yeah, that kind of thing. You can also impute it. And predictive min matching. This is the most sophisticated method. Yeah. Basically, this is a regression also, taking into account other variables. But this is not stopped after we get the estimate of the variable of the regression. So we may run a few regression. Maybe 3, maybe 4, maybe 5, yeah. But then from this 5 regression, we randomly take a value to replace the missingness. So here, this is not only one iteration. So we replace this, and then maybe several times we do this. So the imputed value will vary, right? We have more than one imputed values. From iteration 1, iteration 2. But this is the good thing, because we have variation in the imputed value. This means our final estimate later will already take into account the variability, the estimate, the variance of the estimates. So we take into account this variance and incorporate in our estimate. Our estimate will be more plausible. Will be more plausible because we are constrained by their neighborhoods. Yeah, this will be 5 or 10 regressions. We will not go away from this. Yeah, so maybe around this one, around this side, but not going to be beyond those 5 regressions. And this is actually addressing the problems of the regression, the usual regression. Yeah? When you do the regression only, and you can imagine where you cannot have negative income, for example, right? Well, a regression is going straight like this, and if what is missing is the lower part of the sample, we may end up with negative income, which is not possible. Okay, And even for regression, we have the one that we are talking is called the deterministic regression, right? Because we only take into account the available data variables and then estimate, and that's all. That's all. And there is another types of regressions. We call it the stochastic regressions. Stochastic regression is taking into account also the variability of the estimates. Yeah? But this still can lead to implausible results. Still can happen that we have a negative value for something that should not be negative. But in the predictive mean matching, because of the constraint within this environment of the neighborhood, yeah, the constraint is something like this. For example, we are talking about income, and we have other variables, unemployment, we have other variables, the floor, size of floor, yeah, the house, for example. Yeah? So when this is missing, and actually we are taking into account their housing size, their employment, yeah, and this will not allow us to come up with negative, because when regression are going to negative is constrained by this neighborhood. So this is predictive mean matching. So we'll look at the mean around this given this level, yeah, mean given the same level, and then assign it. That's why we call it predictive mean matching. But this is actually the best method, yeah, the best method. And those so far are talking about single imputation. But we can have the PMM, predictive mean matching, or we can have regression, stochastic regression. We can have deterministic regression or mean imposition, etc. Within the algorithm of multiple imputation. So the imputation is not done only once, but several times. And I will give you an illustration so you can imagine. I think a bit after this. Yeah, okay. This is the algorithm which is allowing us to have several data sets estimated. And then from this data set, we improve our imputation. It's called MICE, multiple imputation by chain, without ED, chain regression. Yeah. Multiple imputation, what should I say? Oh yeah, when I say about selecting representative of the group data set, there's so many data sets. Yeah. This should follow the Robbins rule. They call it Robbins rule. I don't know how this. This Robbins give a formula for estimating the total variance. Yeah, and total variance is composed of the variance within the regression itself and variance among the different kinds of regression that we have estimated. Those two kinds of variability is taken into account. So this improves the regression. So you'll see the result of this kind of algorithm. If we use the regression, it will be in a straight line, yeah, straight line. But if we use the PMM, it will go straight anywhere it can be, but not in a straight line. So may represent better the situation. Okay, so the mice is just an algorithm. It can be used with any methods of imputation. Summarizing the impact, the missingly completely at random, there will be no bias. Even if we delete the missingness, no bias. But the variance become high because we have smaller number of observations, and then the MAR still biased, and variance is still high also, because normally the imputed value is somehow is smoother, yeah, not really representing the variability of the sample. And the MNAR also will be biased in high variance. And if we do data imputation, the variance can be reduced, and bias also can be reduced. But for the MAR, actually we can have no bias if we apply the proper one. So this should encourage us to do some imputation, especially later after I show you the methods in action. Yeah. So, but now let me show you the illustration of this algorithm of the mice. Okay, this is mice, but using the regression method. This is a very simple data set. Yeah, we have age, experience, salary, and the amount purchased. Yes or no, yeah. Whether he purchased this product or yes or no. And we have missing value here, experience, salary, and age. Okay. So what they did is that we the very first step, we impute this value, the missing value, using the mean. And this is the mean of this regression, these values. 7 is the mean of this, and then on the right also the mean of this. So this is just the first step. We have to improve this, yeah, because of the simple approach, of course, yeah. So how to do this? We do this line by column by column, variable by variable. So we drop again this value, and we use these two variables. Yeah, these two variables to estimate the regression. Of course, 3 variables regression. Age, right? Here. Age is a function of experience and salary. Okay, then we can predict the age. If the experience is this much, salary this much, the age is here. Okay. And then second step, we drop the experience. We use this one. So we use this data, the complete one, to estimate the regression coefficient, and then based on the 25 and 50, we estimate this one. You got this one. And then next, we estimate the salary missing value. Again, the same thing, using the same regression where salary now, I should say salary here. Salary is a function of age and experience, like that. So we have complete numbers now, complete data now. But this is not all. This is just the first iteration. Okay? First iteration, because if you take the different, for example, do I have it here? I don't have it here. But you take the difference between this estimate, final estimate, and the first number that we get, this one. Is it?
Excuse me, Mr. Agus,
Yes.
I have some question.
Yes, please.
After we imputation the value of missing data, in this slide, we got the numbers, for example, in age variable, we got 36.25.
Okay.
My question is, we need to round the number that we get from the imputation or not?
Yeah, and
I mean, most of them is a whole number, but the value that I get from the imputation, we got a decimal number.
Yeah.
We need to round the number on that.
At the final stage, yes. At the final stage, but at this first round, we'll leave it there because this improved the accuracy, right? The precision. So we leave it there. But later, after we got the final figures, we of course rounded them. Again, back to here. Here you are. So this is the result of the first iteration, right? 36 point something, 1.872. Oh, by the way, you can, this also illustrates the problem. Yeah. This for people having age 25 and salary 50, experience is only 1.8, which may not be really plausible, yeah. But still move on. We take the difference between this first round estimate and the input data that we have. This is the one we imputed through the mean, yeah? The mean imputation. Yeah, mean imputation. So we subtract this from this, and we got this number. 0, 0, 0, of course, this is 0 because we don't impute the figures. They are the same, 25, 27 here. But this is the difference. The difference is, of course, still big at the first round. We do iteration. We do the same process to this one. Same process. We delete again 36.2537, and then estimate the regression, then put again the number. Then delete the 1.8, estimate and put the number. Then next here, yeah, etc. And so on until we got the acceptable difference here, until they converge. Okay. So this is more or less the what they call the mice. So first iteration, repeat the same thing until we get second iteration, not change to 34, yeah, and then go on and on until we reach some convergence. So we provide in the algorithm in the R either the maximum iteration number or some convergent level. Yeah. So, okay, if you reach until this much different, then stop. Or if you reach until this times of iteration, then stop. So this is more or less the mice, but this is using regression. So the more powerful one, if we use the PMM, predictive mean power, not using this regression. Yeah. So we can use this kind of regression. This is the deterministic regression, or we can introduce the stochastic regression, or you can introduce the PMM. Even if you want to use the mean all the way, it's also possible. Yeah, because mice is just the algorithm. Yeah, it can just go and run following the rule and following the methods that they are using. So this is more or less the algorithm of the multiple imputation chain model. Any question again before we move on?
Pak Agus, may I have a question?
Yes, please.
On the second iteration and maybe third or maybe fourth iteration, how do we know that our iteration is the maximum iteration? How do we know when we stop to make iterations?
You'll see in the R, we set the maximum iteration number. So maximum iteration maybe 20, okay, and they stop at 20. Okay.
Yeah, and I mean, how do we know what number we should put? As you mentioned, you mentioned that we can put 20 or 15.
That's right.
How do we know how we decided?
Yeah. That's really intuitive, yeah, because also depending on the data situation, how smooth if they move together, if they moving very widely, maybe we need to have a longer iteration. But normally 20 is a common number people use. Yeah. I cannot answer exactly, but yeah, depends on our data. That's really intuition. That's why I said the people from the member states should be the best to do the imputation because they know their data very well. So maybe, just 5 iterations may be enough. Or if you would like, then you can do the same. You can trial and error, yeah. Just increase from 5 to 6. So how they differ. The difference is still substantial. You go again. But if they don't change much, then you can stop. Maybe that is a more pragmatic way. But better again if you have some idea of the behavior of the variables, the data. Okay.
Yeah, I see any more question on the chat box, Pak Agus.
On the? Oh, okay, sure.
Yes. I can read the question for you.
Okay. You?
Yes, may I know what percentage of the missing value acceptable?
Yeah. We are statistician, you always go with 5%. Yeah. So there is no rule, but the rule of thumb is 5%. So normally, and 5% is missing, especially when they are meshing completely at random, then we can omit this messiness because we still get an unbiased estimate, and the variance may increase, but maybe still acceptable. But if the messiness is until 20%, 25%, so you have to be careful in terms of the variance, although the estimate is still unbiased. Yeah. So rule of thumb is 5%. So
yeah.
Anyway, yeah. This.
Yes. There is more question, I think, from colleague from Brunei.
Yes, please.
From Brunei raising hand, please.
Yes, please.
Okay. Thank you, Hanik, and thank you, Pak Agus, for your presentation. I would like just to probably seek your advice. I have two questions actually. The first one is, in your opinion, what is the best imputation method for non-respondents to census or survey of enterprises? If there is time series data, so that's the first case. And secondly, if there is no time series data. And my second question is, how detailed should we do imputation with respect to ISIC? Is it at how many digit level? Yeah.
Okay.
Thank you.
From the last question first, how many digit level? This, of course, depends on the purpose. Yeah. If you want just to have an analysis or dissemination at 2-digit level of ISIC, then that's fine. But if you want to really get the numbers by 3 or 5 digit ISIC, then you should go that way. Yeah. So it depends on your purpose. And then on the question of whether it is time series or cross section, yeah. Maybe for the data on the industrial production, something.
It's more to census or
The
survey
census.
of enterprises. Yeah.
Survey enterprise. Yeah. Oh, yeah.
Non-respondents. Okay. Yes.
Yeah. This typically is not a time series. Yeah. Maybe what you say is that you have many data in several years or several quarters, right? But not really a time series data. It's really having the same interval of time. Time beta is always having the same interval of time, monthly or quarterly, every time we have. But if you have, for example, 20 years, but the figure is 2005, then 2008, something, maybe this is not the time series yet. But anyway, for the real time series data, we have some special method that I will show you. Normally it's simple, yeah. But for the data with some years of availability or cross-section, you can apply this method. The best to me is if you do this with what do you call it, the mice, yeah, mice, and the method is PMM. The PMM avoid us from having the implausible one. But the most important thing, actually, my advice is that as you see in the simple example of regression, yeah, we should have in mind actually several data or indicator which are more or less should have some coherence among them. Yeah. So basically, you want to estimate this. taking into account other variables in a way that they will be somehow, there is some coherence. You cannot get the right number, of course, but at least the figures are in coherence with the other variables. That is the importance of this multiple imputation. Yeah, but you use this mice, but using regression. The problem is again there is a possibility that we have some implausible number. But the PMM is I should say ensure us from not having plausible figures. Again, because we are constrained by the vicinity of the data. Yeah. We estimate this, but taking into account the other information of the same respondent or of the same company related to the missing value. If income is missing, then we should be able to estimate income. If we know, we have information about the number of production value, yeah, on the employment there in the company, yeah, etc. So we will not go astray, not go beyond the implausible range. Okay, did I answer your question?
Yes, Pak Agus. Thank
Okay,
you.
thank you. Okay, thank you. Any other? Let's move on then to
I see no more question on the chat box, Pak.
yeah, thank you. The next presentation, I still have time, is on again on the missing values, but now the methods, but now we are more of illustrating this in terms of the R, yeah. Okay, we will be using the data, this air quality data. We'll be using air quality data. Yeah, and this is just a background. Air quality data is the data set about the New York City air quality 1973, and this is the how they observe here. Some of them measured in this area, some of the area, but we have that data in the R. So this normally used in the training. So that's the content of the data. And okay, what is this? Okay, yeah. This is my note, just to be sure that when we load the data, and then better to copy it. Yeah. So we don't do damage to the data. We're just using the copy. Very easy with this. So if we in the R we set digital air quality, we load them, and then we copy by calling that please put this air quality to the DAQ, data frame of air quality. I call it DAQ. So maybe I should show the R. Air quality. Let's see one by one. Oh, here you are. This, yeah, if you click this, you get the data loaded here. And then you copy it, EQ, then you will be safe. You have the other data. Yeah? This is the data. Click this one. Ozone, solar radiation, wind, temperature, month, day. You see this, there are NAs here, missing values. Okay. So we would like to know how much, how many, and then what is the distribution. Okay. Go back to here. But I have notes a lot in this PowerPoint, so I don't want to lose my note also. You better read the notes also. You're not just following the script. Okay, this is the data that I showed you. AQ data, copy data. The head, I think we are familiarized. The head, you get the summary, the top 6, yeah, the top 6. There are NA here, even at the 6th line, so there must be a lot of them. But how many? Okay. First, also we can run the summary. Summary, we got the summary statistics. Again, the minimum value, median, etc. And here we see there are 37 NA under ozone and 7 under solar. Okay. And the other, we don't have any missing. So here, how many percent are missing? Percent missing. But first, actually, this is not the code for that. This is the code to get the complete data. Remember in the algorithm, I mentioned several times, we use the complete data to run the regression and then to estimate the missingness. This is the code to have the complete data. So if we run this, I call the new data frame, I call it DAQCC, yeah, complete case. Use this one, and I got here the data in my environment, the air quality data CC. You see the number of observations down to 111 from 153. Yeah. This is the data, and then this actually another function you can use, same as the one you just seen. You can also have the complete case by using this statement, this function, yeah, they call it function. You run this and you got the DAQ, no miss, I give different name, yeah. And then the other one is DAQCC. They are the same data. Yeah. Okay, now if we this is a summary. Yeah, see the same function here, same function. I just say that the complete case can be obtained through this and this. And this is the result. We are the same. Same. This is the name of the data set. You get the same number. But what is important now is that if you, for example, run a regression, yeah, using the air quality data. Let's see what happened. On the second thing, back to here, and you run the regression using the original data. Yeah, I just want to say that in many, or actually most of the program, they by default they remove the messiness. Yeah, so that's why they can have the regression. Otherwise, they cannot because there are NAs, right? So they remove the NA by default actually. So this we will get the result from this, and this is just showing you if you run also regression 2, yeah, by intentionally remove the missing. So you can add this function, and then second regression, if you also run the regression of the original data, but not using default, but here, in fact, you intentionally retain the NA. So this is false to retain the NA. This is true to remove the NA intentionally. So we'll see the result. Regression 1 is fine, yeah, because by default the program already removed the NA. Regression 2 also fine because we intentionally remove the NA, but regression 3 is unsolved. Why? Because we intentionally retain the NA. So there's still NA there, so the regression cannot be run. Okay. I think we have discussed this regression method. Let's see. Mean imputation. This is the way we do mean imputation. Yeah? We impute, take the mean, in each variable that are missing. So for that, we have to install this package, mice package, and then of course to load the package library mice, and then this is the instruction and the code for imputing the mean. Yeah? This is the name of the. This is metric, or this is metric. Yeah, data frame. Apply this method and this algorithm mice to the data DAQ. We don't use the original data, yeah, because I'm afraid to change the data. So the method is mean here. Mean. The mean, then we set the maximum iteration 1. Why 1? Yeah, because if you compute the mean, how many times you impute, they will give the same mean, right? So just 1 is enough. And M1 is the number of data set that we would like to have, yeah. Because there's no advantage of having more than one data set, yeah. Because we have the same number, mean. You mean just the mean. So then we put everything here, and we get this data. If you remember, line 5 was missing. Now we have, can you see it clearly? Or, yeah, line 5 was missing. So this is the imputed value. This is the mean of all of this. Also, line 6 and 5 of solar was missing. So the imputed value, of course, the same, because the mean of this variable only one, yeah, 185. They're the same. So this is an illustration of the mean imputation. Okay, this is another statement for mean imputation. Okay, problem. If we don't use the mice, you can also do the mean imputation. Yeah? But we have to do it column by column, variable by variable. So this is for the ozons, this is for the winds, this is for the solar, yeah? This is for the temperature. And line by line, you can do this, but with mice, you can do it more easily. This is the result, same results. Yes. Regression imputation. Yeah, regression is considered as smart imputation, yeah, because it takes into account other related variables. That's why in our imputation, when you want to impute it by a regression method, then we have to make sure we have a set of variables which are at least having some correlation among each other, yeah. So when this is missing, we can look at the other variables. So just like if we want to do some regression, we have to have some kind of concept in mind, some kind of relation in mind. The same thing here. So I mean, not just to put everything in the imputation, yeah. Of course, it will work. Everything you put it there, and then you will get the number. But of course, you don't see the logic, yeah. Regression by mice, using mice, is the data where we want to put the results. This is the data we are using. Where is the regression? Here. This is the statement. Yeah. You use mice here. Use mice. There's an option for the method. You can use the norm predict. Norm predict is the deterministic regression. Deterministic regression. And because mice again involve several iterations and will choose the representative of them randomly, so we will have to set a random seed. Otherwise, your estimate can change every time. Yeah. So you set the random seed. This is the initial random number. You can set 100 or 99 or anything, but you set this, and then next time you run again with the same number, you get the same result. This is the statement. If you have this complete case imputed already, yeah. So you use the complete case as I illustrated. Use the complete case to do the regression, right? And then you put the information to the imputed delta frame. So this will give us the output deterministic regression. Yeah. So we get this data. Next scene. Here what I have mentioned earlier. Have we used deterministic regression? Our imputed value are more or less in straight line like this. The red one, the red one. While our actual data, if you look, the variance are increasing. Yeah. But the regression, the imputed value is still here, not really reflecting the distribution of the observed value. So this is one issue of the regression. And as I mentioned also, when you are imputing someone or some observation near zero, if the regression is going this steep, and then you get the minus number. So this is not possible. Yeah, this is the message from the experts that using regression can be sometimes very dangerous. Yeah, because again we are so confident. We thought we are so confident that the regression is best, right? Best. I have the best estimate, but if you see when the real data is like this, the regression estimate cannot well represent the data. This is for the deterministic regression. So people want to address this by stochastic regression. Yeah? Stochastic regression, they incorporated the error term in it. So it becomes stochastic. The regression is no longer straight line. Here is the function, yeah, method equal to norm and OB. And OB is this is bias. The B is bias. Yeah, this is an OB. I forgot the extension. And let's see what happens if we do this. We got different estimate. Yeah. Of course, you will not be doing this. Yeah. Checking one by one like this. You will see later the summary. So this is just an illustration. And here, if you can see, the red is the imputed value, can go representing more or less the observed value. It's not a straight line anymore. You can go here and there, yeah, because they already take into account the variability of observation in this area, for example. So you can go up here, and the variability of this area, so you can go a little higher. So it's much better than the deterministic one. So it is advisable if you want to use regression, you use this NOV method. Now here, look at the extension here. Non-Bayesian. Non-Bayesian. NOB stand for non-Bayesian. But this stochastic, yeah, stochastic, but still non-Bayesian, still incorporating the variance of their own data. Yeah. And now we can move on to the next. Next method. Let's apply. Oh yeah, non-Bayesian. Apply the last observation carried forward. Yeah, taking from the last observation, or the what is B? Baseline observation carried forward. This is the B. This is the statement. And let's see what we get here. This is 1818 because we use the last information. This is the 15, 18. Okay, this was missing. And then we take this value go here. This was missing, and it value goes here. Okay. And now what? Multiple imputation. Multiple imputation, as I mentioned briefly, that it involves iteration. And so we have more than one data set, yeah. They call it M1, N1, yeah. So the data set is not only one, but can be more than one. And then the selection of the candidates for the best for the imputation should follow the Robin's rule, yeah, which guide the selection based on the standard error. This is the example of what is this? Multiple imputation, yeah. Mice, okay, is a mice, right? And then you can ask for 20 data sets to be produced. 20 data sets to be produced before they come up with their choice, yeah? So it's a lot of process inside, but we don't know actually. But I think the illustration that I gave hopefully can help imagine some kind of process. So when we do this, we got this regression estimate that they are using. This is the pool one, yeah. There are many regression, and then they select one of them randomly, and then considering the standard error extra. This is the selected one, and this is the results. If we are using this multiple imputation, Okay, this is just the regression estimate. Okay. Okay, I think more information is available on the next one. Okay, more example. Okay, this is, you will find some more codes which may be necessary for your uses. This we are using iris data. The iris, and then we copy this data, iris C, this is copy, and we ask the summary as usual. And we compare the iris and the iris C, they're the same data. This is the summary, as usual. There is no missing value here, right? No missing value. But for the sake of exercise, we want to create missing values, introduce missing values. So this is the statement. You can introduce NA to our data set and then try to improve it, to impute it. Yeah. Later you can compare with the actual one. This is a good simulation. So this is the statement to produce the number of NA until 10%, 0.1. If you want 20%, you put it 0.2. But you need to install this package, the mesh forest package. Install, and then load as usual, library, and then you draw this. Of course, you want to assign the NA randomly, randomly. So you want to draw a random index number, and then to this index number you put the NA. So you need to set the random seed, the initial random number, in order to for you to be able to reproduce the same value, the same estimate. Yeah. Because if you change this or you don't have this, when you change this, and then the selected cell that you will assign the NA will be different. Okay, when you repeat it. So here, plot NA, then number of NA 10%. Yeah, please produce the number of NA 10% from this data set, and then put it to this metric, this data frame. So if we click summary of the data frame, this is the summary. We see NAs here already introduced. 18 here, 15 here, 11, 15, 15. They are not the same because they are assigned randomly. Yeah? But on the average, this is it 10%? Yeah. Sorry, maybe more than 10%. Okay. Oh yeah, 10% of course, because the number of observation is how much for the iris? 150, right? 150. So 150, 10% is 15, right? Average. So this is 15, this is 11, yeah. The average is 15. Okay. So you can see where you put the NA randomly. Here and there, and in the next rows. Now you can check. I think you've seen this function, you can check the number of NA by column, column sum. So ask the R whether it is NA. If NA, then compute the column sum, and this is the percentage. So this one divided by the number of rows. So we can have this. Why is this 0 or predicting 0? Because we use the original data set. It's not mentioned here. Of the complete case, here. Of the complete case. If you use the complete case, remember the complete case is the metric, the data frame, where we already removed the NA. So of course NA are 0 here. And we use the complete case. But if we use the one with the NA, and then we got this number as we've seen before. Why is this error? Okay. Okay, I'll check why this is error, but this is the result if you do the column sum, column sum. And this is the same thing. This is the same thing, same statement. So that's why you're producing the same thing. And I don't print this one then. But this is another statement, another function, not by column but by row. We ask how many NA by row. So in row 1 we don't have. In row 2 we have 1, row 3 we have 1. And this is, I don't know what row, but they have 2 NAs here. And here, another row, there are 3 NAs, something like that. Or I put it here. Okay, you can read it. Okay, this is where the NA are spread. Again, this is the complete case. You want the complete case. This is the statement, and you got the complete case. And you get summary. There's no missing because it's complete case. Okay, now what I want to show you. Oh yeah, we here can remove variables which are not numerical, because we are going to use them in the imputation. So we don't use the categorical variables, right? So like in this case, the iris, we have simple length, simple width, petal length, petal width, and then species. The species is the categorical variable. So we remove that, by this instruction. Select. This is the minus sign. Minus sign means without species. Into data frame, the DFN and IRIS-N. Let's see what happened. Here we have for DFN. Now we only have 4 variables because we have removed the species. And then the ISN also we have only 4 variable, but remove the species. This is the brain. We don't have species here. Now with this complete data frame, we can do the mean imputation. We can compute the mean, because if we use the whole set of data, then we can get an error. Yeah? So we only use the complete case. To compute the mean for one by one, of course. For the simple length, this is the mean, and the simple weight, little length, little width. And then we print them all together, simple length, simple width, length. And let's see, yeah, this is the result. This is the mean coming from the complete data set. Okay, so this we can impute it to the missing value. So it replaces the missing values with values of the mean. Yeah, describing this method. As mentioned in general, is the most commonly used because it is easy. But again, we have to mindful about the distribution of the data in that variable. If they are more or less mild distribution, maybe it's acceptable. But if the data are really fluctuating among themselves, then it's not good. This is the same thing as we seen in the air quality data. If you do the imputation without mice, this is the code. Yeah, you have to compute the mean. First, you have to remove the NA, and then you have to compute the mean by variables, and then impute it to the data frame. The mean here we got from the completed case and put it to the data frame, and you got the estimates. Yeah. So, but why bother this? Because we can use the mice actually. Right? Mice is much easier to use. You can, by the way, you can look at this document. I really prepare this for you want to really see the results step by step. Yeah. Multiple imputation, theoretically I have mentioned, but then the example with the mice. Here, if you use mice, again you install mice, and then you impute. This is the statement function, mice, and then the data frame, what data you use. Method is my min. This is min. You get the number. You can compare with the previous one, with the one that is manually done, should be the same. Yeah, by the way, if you do the mean imputation or any imputation, and then you can click on the methods, and you get this information. So the method for simple length, simple width is min. Yeah, min. If you use the regression, it's also here. You can check what method you are using. PMM, I have given you some ideas. And if you want to use PMM, give the name with the extension PMM so I don't confuse with others. And this is mice. This is the data that we'll be using. And the method is PMM. you have to assign the random number. Can be any number, but should be consistent. Every time you don't change the number, yeah. Then maximum iteration 50. So here, actually, in this kind of algorithm, we only set the maximum iteration. So I don't know if there is another way of telling R the convergence level, yeah. But this is easier to use maximum iteration. And Hanik asking us, somebody else I forgot how many we should put here. Can be intuitively depending on our understanding of the data. Yeah. If saying 5 times is sufficient and given no big change from 4 or 5 or 6, then maybe just stop there. But if the data is fluctuating, maybe bigger number is required. Yeah. So if you run this only to here, of course you get the imputation, yeah, but you don't see the figures. You have to put the results in the data frame here. So if you click this one, you can see the results. This is just a summary. And using PMM method. Using PMM method, we see no more NA here. You can scroll down the whole thing. You can see no NA. But here, if you recall, one of the species is missing. And PMM can do the imputation of this categorical variable. Other methods actually can do this, but you have to change this into a factor, yeah. So maybe species you assign number 1, and then Sitosa number 1, and then Versicolor 2, Virginica 3, like that. So it has to be a numeric. But in this PMM, we can have this as it is, and we got this Sitosa imputed. The imputation never get right every time. So look at this. They give here versicolor. Well, actually, this should be Virginica. This is all of Virginica. So maybe wrong, but for this we can, of course, correct it. But the whole thing is not imputed, including the categorical variable. And here again, the summary of method, you can see the method. I don't collect this. PMM, yeah, all are PMM. Predictive mean matching. This is the norm predict, non-Bayesian method. Okay, we try all of them. Then I have the chart, no? Yeah, the chart we have seen in the earlier examples, but the predict, yeah, this is the right, the straight line regression, and the imputed is in the straight line, and then the norm and the non-Bayesian one, and we can see the imputed value varies not in the straight line. I would suggest you go over this slowly, but of course we don't have time here. Okay, let's see if we have time. What time is it? Okay, we should break first, and then I will show you the R.
Yes, Pak, we can have a break first.
Okay, and maybe the quiz. Are you ready with the quiz? Okay. Maybe 3 minutes quiz.
Agus, it's been 5 minutes and we have 29 participants who have answered. You want me to end the poll?
Okay, I think it's fine. Yeah, please conclude.
This is the report.
Okay, it's very good. MAR allows to impute missing values based on what? On educated guess is known. Other variables or column in the data set. That is the correct answer. Yeah. Because MAR again, the kind of missingness which is related to the other characteristic of the respondent, if this is about the survey, related to other characteristics of the same coherence framework, yeah. Meaning if you have GDP, poverty, and then, for example, unemployment, those are within the same coherence framework. The GDP growth is not performing, and then the unemployment is increasing, so the poverty must be increasing. So that kind of framework of coherence should be available, and with that kind of framework, actually we can use the information to impute the missingness of one of the three variables. So allow us to use other variable to do the imputation. This is the MR, missing at random. The unobserved, this is some observed, 28%, yeah. Only affect the case of non-missing at random. But if we have information about unobserved, but this is difficult, yeah. The cause is unobserved, then one strategy is for you to do some kind of comparative analysis. So you do the sample with the existing computer tablets for the enumerators, and the other one with the new tablets. If there are big differences, you can conclude that, oh, this is related to the tablets. Yeah. This is unobserved, because this is unobserved. Also, the anxiety maybe can be approached by the maybe the age or gender still related to anxiety, but basically this is unobserved. But this is related to the MNAR, yeah, MNAR, not MR, not MER. Number two, which method allows for the use of other variables? Oh. Which method allows for the use of other variables in imputation? Okay. Similar. But this is referring to the method, whether deterministic, regression, mean imputation, and stochastic regression. So the answer is A and C. Yeah, the correct one is A and C. You're instructed to have one choice only, so maybe that's the problem. But the correct answer is A and C. Yeah? A, deterministic regression. You can also use the related variable for imputation, and then the stochastic regression also, but not mean. Mean imputation is only using its own time series, its own data. Yes? You cannot use the mean of poverty to impute the GDP, right? So you only use the GDP data. So we use mean imputation, you only are using that particular variable of interest. But if you are using regression, you can take into account other variables. Okay, that is number 2. Number 3, the MICE algorithm allows us to ensure plausibility if applied using weights method. Yeah, number 8 is the correct one. Mean imputation can be very implausible, as stochastic regression also still can lead to some possibility of having implausible results. Okay, I think this is pretty good. Thank you very much. Tari and colleagues, maybe you can go for a break now. Come back at 11 after 15 minutes after 11. Okay.
So
Yes,
we will back at 11:15, Pak.
Yeah.
All right. Okay.
Thank you.
Agus. I think we can continue the session for today.
Okay, thank you. Any question before I continue?
I see no question on chat box.
Okay. So I will show you the R, which I don't think I have seen you the whole thing. So maybe a bit slowly on the missing values handling with mice, yeah. So maybe we can get more familiar with this. The script I could not find, but I will copy this to you. I'll be using the air quality data that we have discussed from the slide, yeah, from the PowerPoint. This is from the R. I'll show you step by step. And then after that, we'll go to the missing values for the time series. Clean this up first. Okay. So we'll be using the air quality data again here. Just this statement. And I got the data here, air quality. You click, you can see the data. You cannot see whether there are missing values. Oh, there are here some. Again.
Sorry, Pak Agus, are you showing your screen?
Oh, sorry. Sorry. You should have told me earlier.
Yes, we cannot see it, Pak.
Sorry. Where is the... Okay. Now, can you see?
Yes, yes.
Okay, sorry about this. Again, we will be using the air quality data, and I'll show you step by step on the R. While we further reviewing to get us more familiar, and then we can go to the time series, missing values in time series handling. Here the script is called, what's it? Script? Missing value basic, yeah. So I think I have the script already. Okay. Have you load the data, air quality? This data has been in the R, so just call it data air quality, and then we get here air quality with the data. You can click this and force it to the data frame. Yeah. And we see some NAs here. Yeah. But of course, we want to know how many of them. And here is always reminded, we copy the data first. So put the air quality data into this object. Yeah. Object is the data frame as well. So let's run this. And I got this copy here, exactly the same dimension. It is just the summary as usual, but we need to see the NA. So NA, yeah, 37 on the ozone, 7 on the solar, okay? So we have a problem with the NA. And now the title is not correct actually here, but this is about the complete data. The complete data. When I say complete, it doesn't mean the whole thing, yeah. And this term, when we say complete, this is meaning that the data with the complete values, nothing, no missing, no missingness. Okay? So we can create the metric, the data frame, with this statement, complete case, yeah, with this function, we call it function. Yeah. Here is just to mean that we want the entire column, and this is the row, because when we select is by row, yeah, by row, we remove the NA by row, but please retain all the column, like that. So run this, we got still 6 column, because we want all of them, 6 column, but the row is down to 111, yeah, because of the missingness. And now this is the correct title, how many percent are missing. So I've seen error in the PowerPoint, right? But I don't know why, but this is correct. Maybe when I was copying to the PowerPoint, I was just made a mistake when still appear there. But this is correct. If I click, yeah, 37 and 7, and 8, and this is the percentage. Okay, so you can use this to no worry. There's no error in this script. Okay, and then this is another statement to get the complete case. Yeah. So this is the same as the one we have above. So you can choose either one. This one, complete case TAQ, or this one, omit the NA. Same thing. You want the metric with NA omitted, or you want the metric with complete case. With the definition of complete case is without NA. So this and this one are the same. Okay, but let me click this. You got the TAQ, complete case, and then the TAQ no missing. They are the same. So just use one if you want to do your own. But this is just for the sake of showing you the various way of doing things. Okay, and okay, this is another one. Alternatively, in the previous slide, I can use this one. Okay, this is the same as the one above, I think. Yeah, same thing. I don't know why I put it 2 times. Okay, let's click here. Oh, it's here already. Yeah, maybe just a repetition. Okay, now let's go to regression. And we use the, we want to estimate the regression. Actually, there's no issue, yeah, because the default is they will remove the NA. Yeah? But this is just showing you when I run the regression with default, and the other one I run the regression with retaining the NA. Or I run the regression with removing the NA intentionally. So it's just to show you that in case you want to remove the NA or to retain the NA, this is the statement. Here the regression is applied to the, what data is this? Air quality, yeah, apply to the air quality with default. I didn't see anything, and then give me the results here. This is the regression. This is estimate. Standard error, yeah. But if you run it on the complete data, same complete data, and intentionally remove the NA. So this is the code. If you want to intentionally remove the code, although you don't need it, yeah. This is just the omit. You put it through, and then if you run it, you got the same regression compared to above, yeah. You can compare it. And the next one is if you retain the NA, yeah, just to show you that there is NA there and you retain it, you force it to be there, and you run the regression, you get an error. So this is error. Yeah, you cannot do this. Okay, and now review about the mice. Mice applied to the mean. Even mice, you can also use the mean method, yeah, with mice. No problem. The algorithm still mice, but you can also use the method of mean imputation. First, you have to install mice package, because I have done it, so I just go to library. I want to show you what happens if I still click this. See, they're asking me whether to continue. You have installed it, so I said cancel. And then load the mice. Okay. And this is the code for doing the mean imputation method using the mice rhythm. So you click this, you get the results. Yeah, one iteration, one imputation. Yeah, this is the one that is imputed, and you can see the result later. What else here? Okay, now alternative way. Of course, you will prefer to use mice, yeah, but this is not the way, and the codes may also be useful when you're doing something else. Yeah? But to do the mean imputation with the other methods than mice, you need to install dplyr package. I have done it, so just library, load, yeah. And to do the mean imputation manually, I should call it manually, yeah. You're not doing the mice, then you do it in an ad hoc way. Yeah? First, you have to remove month and day. Yeah. Why we have the minus here? This means do not include these two variables. Yeah. Select the column, but select is for column. Yeah. Select for column. But filter is for row. Select for column, row. and select, but do not include month and day. Yeah. And then you put it this air quality numeric, and this stands for numeric. I don't write here. I'm a bit confused. Oh, sorry. No. Stop. No? Oh, yes. Okay. Let's run this. We get the data frame called DAQ. Data frame air quality N, yeah, air quality N. Data frame air quality N. And this one. Now we only have 4 variables, but we remove the day and the month, not included in the imputation. So this is the codes you do imputation, not using the mice. Okay. For ozone, of course, Na, because there are Na, you cannot have it. Yeah. But this you can have. And then next, this is where you compute the mean for each variable from the data set, yeah, of which the NAs were removed per day. So when the NA has been removed, you can compute the mean. Right? So you will compute the mean for ozone, for wind, for solar, and for temperature. Okay, no error. Yeah. And then we go to deterministic regression. And don't think I've shown all of this, but let's see. I've seen you the deterministic regression with the non-predict. And this is the statement. So we are back using mice, yeah, using mice, but this is for with the method of regression. But this is the deterministic regression, predict. So we click. You have seen this one. And this is the result, where the imputed value is along the straight line. Yeah, it is not really realistic. And then this is the NOB procedure, which is the non-Bayesian. We have seen here Bayesian, and let's see if still okay. The scripts of non-Bayesian. This allows for some variation, yeah. Some variation, so the result will not be a straight line. Okay. See, the red is not on the straight line. This is more realistic in a way, but still, again, having some possibility of implausible number like minus. Yeah. On the case where there is no minus. Okay. Yeah, I did then multiple imputation. But I have not seen the other method like the PMM and set here. Okay, no. Yeah. Oh, yeah, maybe I mistakenly remove the codes, but I produced one here for predict for the regression line, linear regression, and then this is for stochastic one, and I produced for the PMM. PMM shows the best representation of the data. I will correct this codes and then provided you with that. Okay, that is what I want to show you. And now, if there is no question, let's go on to the time series analysis. Missing values on the time series analysis. This one. Okay. Yeah. For time series, this is kind of temporal property, having a temporal property. Yeah? I mean, it moves by time, yeah, over time. Moves over time, and we have the data ordered by time. This is the time series. For that, today we don't have much method, but we still can apply even the mean, the median mode, yeah, and random, and also of course the regression. And here you can also introduce, they call it the random method to assign the value randomly. And then I will show you that if we combine the mean and the mode and this kind of ad hoc measure with the proper regression, and then we can have a better result. Don't want to repeat this. We decompose, we have this kind of component, and yeah, this is if you are using the non-time series specific method, yeah, mean, imputation, median, mode, we can still use that. This is appropriate still if we use time series but already stationary or near stationary, because you have a trend moving up and then you only use the mean to impute some values. This may be up there or down here, and then it's not be realistic. But if it is more or less stationary with little variation, then of course still make a good sense. We need to install this one library to install the Impute.ts. But if you have installed and then just load it like this. Okay. Here, I have to inform you first if you use that script, yeah. we are using the air passenger data. But for these purposes, on this air passenger data, some data have been removed, yeah, considered as missing. So if you see here, there's missing values, yeah, in some areas, but this has been removed. Initially, this is complete, yeah. And you have seen one way of assigning NA, right, to our data using the prod NA. Right? So you use the prod NA and introduce 10% or 20% of NA to your data, and then you can see if there makes sense if you make an imputation using the mean on extra. This another statement of summarizing the data to show the NA, yeah, to show the missingness, and this give more information, and they group it into bin, like box, yeah. Bin one, you have values from here to here. There are 4 NAs. Bin 2, 1 NA, etc. This may be important if you want to see the distribution more or less. This is another more information, the longest NA gap, yeah, may be useful. Okay, now we want to see the codes for running imputation using mean, median, mode, random, and for using the combined method. Here are the codes. So let's see on the R whether it works. Close, clear all of them. Okay, in my case, I'm still in the directory P5, missing values, where I have this time series imputation, and we have the imputation for the iris data, and then the one on the air quality data. So it's convenient when you structure your directory like this, yeah. Because if you don't, and then when you open one script, and then the whole content of your RStudio is there, so you will be confused. Even me with the little number of R script is already confusing. Okay, this, let's see from the beginning. And again, we have to install this one. I have done, so just did I click? Yeah. I just load the package, and then I plot the data with air gap. Is already the one. This is with the gap already. Gap. This is the one that you have seen with some missing. And now this is a statistic. Okay, I don't want to run it again. And yeah, you plot the mean and compute the mean and then put it under one metric, I think, yeah, data frame, and then you can print it. So let's run this all together. Until here, you only do plotting. We have to make sure we have enough room, otherwise it's error. Let's run this. Yeah, I got this. The result of the mean difference. I'll show you. Okay, this is what happened if you use the mean, imputation, median, mode, random. This showing the mean square difference actually. Yeah, you take the difference between the data. Remember, you have the original data, right? And of course, this is 0 because they are not imputed. But for the mean, we got this quite big difference. Median also, random also. But of course, this is just to visualize the error. And we can have also them printed in the data frame here. This is the instruction. Here, the mean square error, you got it down here. So you see the random as the worst method. But it's called random, yeah. So sometimes it can be the best, but in this time it is the worst because of the randomness. So the mean is normally actually the best here, but again you have to be careful about the nature of the data. And here was this. Yeah, also plotting. When you see part M pro like this means you are doing a plot and putting all of this together in one screen like this. This is a plot with 2 row, 2 column. So we'll see that we will get the only one. Oh, sorry, I did not include this one. Yeah, this is the results if we use the last observation carried forward, the next observation carried forward, and the linear model and the spline. Yeah. You know this, you take the last value, it's imputed. I mean the last value before the missing, and then this is the next value after the missing is for imputation. Quite neat compared to the mean and the modes. Yeah. Group. Linear also okay, but also again remember depending on the data. But spline performs best. Let's see the standard error, the mean square error. This is how to compile the mean square error. It's been computed here, and then just to print them. We got this measure. The spline function is better than linear and much better than the others. So maybe the trend is Yeah, you can see actually the quite the trend upward, although there are some seasonality. But if you look at here, the linear is still much better than the uh, last observation carried forward or next observation carried forward. Oh, by the way, it's just an error in my typing. Should be O. Yeah. Okay. This spline, I don't know if you know the spline function, but this is more or less, you have the time series data, you cut it into bin and sections, and then estimate section. So this normally is better than having just one line. Yeah. What is this? See. Okay, this is applying the proper method for time series. Yeah, seasonal adjustment. Seasonal adjustment is perhaps the best method. We use seasonal adjustment here, and yes, seasonal adjustment, and combined with other methods. So here, first you do seasonal adjustment, and then random, and then seasonal adjustment, then mean. Seasonal adjustment, then LOCF. Seasonal adjustment, then linear interpolation. So let's see what happened. From here, you're plotting until here. Okay. And again, you will see a plot with 2 rows, 2 columns. Let's make sure they have enough space. Clear this out first. You don't have to clear it, but I will, of course, reduce the memory. This is the results. If you do seasonal adjustment then random, still bad because of the random. So this one and mean, but seasonal adjustment and this one is much better, and then with linear is very, very good. So let's see the standard error, the mean square error. Should put it down so you can, I don't know why I cannot move. Okay. Okay, let's run this. And you get the mean square error. See, seasonal adjustment plus linear, you got only 3.7. This is the lowest so far. Yeah. Earlier we got something 7 or something. This is the lowest. But random, even if it's combined with adjustment, seasonal adjustment, mean also they perform very, very bad compared to the others. So maybe give you some idea that you can use linear seasonal adjustment plus linear or standalone. Even if standalone, or do we have it earlier? No. Okay, we can try later. Add some codes. And then what else? Yeah, I think that's all for the seasonal adjustment. So again, basically, you can also use the ad hoc method, that mean mode, median, and then LOCF. Yeah, that can be used with some caution, of course. And the best thing, of course, if you apply the seasonal adjustment, because that is really the proper method for time series, yeah. So they deseasonalize first, and then do something, and then back reseasonalize, and then to get the imputed data. That's all for the seasonal adjustment for the imputation for time series analysis. Okay. You have any question? Don't hesitate, please. We still have two items. Number one is on the preparation for the country data for your exercise. I will explain. And then secondly, on the exercise on the time series that yesterday you were assigned to, I would encourage any one of you to voluntarily show the results. Maybe inform Tari so Tari can give you the screen. Anyone has done it and want to show, I would really appreciate it. Yesterday, the assignment is to run the time series analysis, ARIMA, and using the UK guess, yeah. But I just recall that UK guess is already in the area, so actually you don't need to load it from your local computer. It's already in the R. But anyone want to voluntarily present this? We will discuss together, don't worry. Okay. No. Okay, otherwise I will show you the results from my screen. This is the time series. Out to ARIMA, UK guess. Sorry. This is what I have mentioned. I wrongly clicked the script rather than project. So here it shows up here in the corner RStudio rather than project 4. So everything within the RStudio is there. All the files are there. So it will be confusing to select, yeah. But if you go by project, it would be easier. So I should have clicked this project before time series project. See, before time series appear here. And here I only show the script within this project. Now I'm going to look for the UK guess, yeah. This one. So again, because this data is already in the R, so you don't need to extract it. You don't need to import it using the code that you have been provided, but just click this and you get the data, UK guess data. So there's only one variable, yeah, but it is quarterly. Okay, 1 to 3 from 1960 to 1986. Okay. And I want to show you the steps for doing ARIMA, which is very cumbersome. And then you need to load this TS Studio. You have to, yeah, and then now you do plotting. First, plotting the original time series. But before that, don't forget to copy. This is to copy the data into this data frame. So I have this data frame, the same content. Okay. And then TS plot is to do the plotting of this data. You can change the title of the USTRA. This is the UK gas, also very strong seasonality, very strong seasonality. Here, of course, the variant is smaller, but then getting larger and larger. So you can imagine you will have running a trouble with differencing this one. Remember, the first step is to make the time series stationary, right? The step is to make the time series stationary. How do you do that? You do the differencing. First difference, second difference, or you take the log if was needed, and then difference, or you do the seasonal differencing, etc. And then check the graph here with more or less it's stationary. This is the statement to do differencing. With like 1, yeah. And then after differencing, you want to put it into the plot. So this one, you put it into this one. This is simpler because this is just a factor, yeah? Only one variable. But if this data frame with many variables, of course you have to select which variable or which column you want to plot. A time series only one variable, so you just put the factor here into here, and you plot it. I check this already? No, not yet, I don't know. Okay, so we have this UKD1, yeah, and now we plot it here. See, the seasonality still looks very strong. So this is stationary in terms of the mean, stationary in the mean, but not necessarily in the variance. The variance still not constant, right? So maybe you need to do what? Differencing, first difference and seasonal difference, 4, yeah? By the way, I should S here for seasonal differencing. So first we difference with like 1, and then we do seasonal difference with like 4, because this is quarterly, yeah. But if it is monthly, you use 12, of course. And we use this variable and plot it here. So let's do this. Oh, okay. Error in statistics. First difference. Oh, yeah, no. Oh yeah, this is without S, yeah? I thought with S. Without S, yeah, it works. And then this one. Not improve, not improve. So you should do more things. Maybe you do the log, this is the log. I don't know whether this is better, but this is closer than the other part of the time series. So this is again seasonal. First difference, then second difference, and then seasonal. Yeah, yeah, without S. Okay, and then we plot it. Yeah, doesn't make much improvement. This is differentiating until fourth time, etc. And you can try. But my point is that you have to make sure that here you got more or less indication of stationarity. Yeah? What stationary, and then you can move on to the next step. So here I have tried many things, but with no significant improvement. Okay, so that prompt us to just go to the auto arima. But before that, of course, if we are doing manually, we have to identify the order of the AR and the order of the MA. Right? So this is just to show you the stages if you want to do it manually. So we do the autocorrelation function. Remember, autocorrelation function will provide indication of the MA order. So we assume that all time series is stationary, yeah? Although this is not really convincing. So, okay, let's stop and say that the time series is stationary. So now let's move on by identifying the RAR order and MA order. SCF indicate the MA order. And then PSCF indicate the AR order. If you shoot the plot, this all are significant. Yeah. So there's no component of AR because this is showing a non-stationary. And then the PACF and this is giving some pattern of the MA and the AR, yeah, the AR. So you can see 1, 2, 3 significant. So maybe the order is 3, or maybe the order is 2. Yeah, if you talk about the parsimonious model, maybe just 2. Yeah, that's the subjectivity. Yeah, included if you do it manually. And then what is T1? If I took the first difference, also try to see if I use first difference, what order of the AR, what order of the NA. Yeah. So I just want to do one more thing. Yeah, this is also not having a cut. Yeah, it's dying out very slowly. And this one is quite clear. Two order two. So okay, maybe let's assume we have finished with that, and then what next after we have the order, and then we'll run the ARIMA. But here we will be using the auto ARIMA again because of this long and tedious and subjective process of doing our own. We need to install this library and focus and time series. Run them together is okay. Clear this. No error. Yeah, red but not error. Okay. And what else? Where are we? Sorry, look the wrong thing. Yeah. So this very simple statement of auto ARIMA. Yeah, auto ARIMA, you can guess. You want AKK and trace. Yesterday, Hanif asked, but normally we use that AKK information criterion. And let's do this. And we got the whole thing. So they tried many models and then pick the best one, which is with the lowest AKK information criterion. Yeah, then 37, and this is the model. And after we have the model, we forecast. Okay. Oh yeah, don't forget to check whether there is stationarity or no in the model. So we run this autocorrelation function and then partial autocorrelation function. Should not show any long dying series, yeah, should show a cut somewhere here. It's not like this, but should be very clear that this is stationary. Also the partial one, you see, yeah, all are within the range of confidence interval. So it's fine. No significant instationarity. Then let's do the forecast. Forecast is also very simple one. We need to have this forecast package, but we have done it. So we just use this. And ask the plot. And this is the result. Yeah? It's quite good, I think. But we should also validate using this. Okay. Okay, that's all I would like to review. Should be not confusing, I hope. Yeah. So if you run the stages, of course, they will be confusing, but the thing is that you should know the process, yeah, and you should really experience the process to really appreciate the auto-arima. If you do it your own, and then there are very, very long process you have to do, and you may not, you're not sure if you get a good model. So let's give it to the auto-arima to do it. So we will get it very fast, yeah, very fast. You can run the whole things, but I would warn you if you run the whole things. One thing, example, you run the whole thing here. Because here you still have statement of install, maybe many, many times. I don't know. And you have already installed in the past, yesterday or last week. So there will be some question. Here apparently is no, because I don't put the install, I think. Yeah, I don't put the install, so that's a shape. But if you have install again, and then they ask you whether to continue, and sometimes you have to abort the session first. But here it's okay because I don't have the install statement. So the same result is here and just one click. Just one click. Yeah. Okay. And we have a few minutes to.
Sorry, Pak Agus.
Yes, please.
Questions coming through the chat box.
Yes, please.
Yeah, I will read for you. First is, how do you write the code for, let's say, for example, UKG underscore D2 and UKG underscore D1 underscore S1?
How do you write the code? What does it mean?
Maybe if there is a rule to name a file.
Oh, okay. No rule. No rule. It's just to make sure you are not confused with the other data frame or the object, yeah, that you are creating. Because if here you have done something with the UKG, yeah, and then next time you want to refer to UKG, then this has been the data has changed, right? So this is a danger. So if you want to perform at the function on this data, and then to save the data in this data frame or in this vector, and then next time you want to do something else, you should give different name. So if you use here still UKG, and then in this case it's still okay, yeah, because we are replacing this every time. But in some cases, then the program not sure whether we are referring to this one or the new one with the new values. But here again it's okay because I do this is not differencing. I just put the original data to UKK, right? And then if you want to do differencing on first difference and put it again on the UKK here, the UKG, yeah, without D. Okay. Of course, you have to change this UKG without D. Yeah, it works, but here when you are doing it works, yeah. But here when you're doing the another steps, you want to use the original UKG, yeah, this one, but because you have replaced the values, then you have a problem. Yeah, so you have to make sure that this is different variable or different object or different data frame every time you make some changes.
Yeah, so basically we can modify it, we can name it whatever we want.
Whatever,
Yeah.
whatever we want.
As long as we know exactly what it is.
Yeah. This is to me is easier. You could do one, or this is first difference, and then seasonal difference. Yeah, you can also write another name, but if possible, it should help you in, because we have so many codes there. Not you will be confused. That's all. Yeah.
Yes. So second question, Pak.
Yes, please.
Can I use linear interpolation or spline interpolation method in order to convert time series for quarterly data to monthly data?
Yeah. Actually, it's not advisable, yeah. Not advisable because you're kind of averaging out everything, yeah. So better to use other indicators that closely related to this time series. Maybe you can use that that movement. You believe they have strong association, yeah, strong association. Maybe you run the quarterly data for these two variables first, and maybe you receive very strong movement correlation among them, and then you can use the monthly data of these other variables to predict the monthly data of your quarterly data. But again, actually, if you want to do analysis, that's fine. Yeah, it's still fine. But if you want to use it as a publication, this may not be advisable. Yeah, because of this kind of makeup data, right? Estimate data. I don't recommend actually, but if it is within the framework of analysis, yeah, where this imputed, or what do you call it, estimated variables is only one among the many things, yeah, and which will be using in the modeling, maybe this is still fine, yeah. But for usage as it is, maybe it's not really advisable. Like this one, for example, we're talking about ASEAN data. ASEAN data, many are missing, right? But we are not estimating ASEAN level. We are missing member state level. Yeah? But this member state level may not be recommended for use by the country as the numbers. But if it is only used for us to provide a more complete and better analysis at ASEAN level, this is still fine. If you want to use it for the national estimates, yeah, of course, this is fine as long as you can also justify. Yeah, I mean, you should also have some other indicators to justify that. Okay, this could be our number. Yeah, and actually, this is what we really hope that member states will try to estimate all the blanks, most of the blanks, their own, with the other variables that are available in your country and with your professional judgment. And then give it to ASEANstats. This is much better rather than ASEANstats doing the imputation, which is only actually for the ASEAN purposes, but and then you use it for the country level. Again, you can use it as long as you can justify.
I see no more question, Pak.
Okay. Now I would like to explain one thing. Very briefly. Yeah, in the first emails that ASEANstats sent you, the request for you to prepare your own data for exercise in the missing values. Yeah, can be the SDG data or SNA data or the economic or social data, no problem. We have provided you with some guidelines. Let me show you. And we give you an example of what we mean by having some coherence in it. Yeah. There are 3 files related to this. You can read them, but I'll just explain the idea and now show you the examples. For example, you are interested in imputing your variable of interest, anything, yeah, but maybe maize production. Yeah. Of course, you can put anything here, any variables, and the imputation still work, but may not ensure that your imputed value here will be in coherence with other related data. So I would recommend that if you want to, for example, impute maize production, and then you have to put within this framework of coherency data like maize in hectare, yeah, and harvest value maybe, and then maybe the horticulture production or hectare, because if there is a problem in the seasons, it will affect the horticulture and will also affect the maize. So there must be some coherence between this, and then maybe the rice, cassava, and anything. Yeah, that using the data should show some coherency. So if you have this kind of framework, then your imputed result will give you some level of coherency, which is actually should be the case, right? So if horticulture increase drastically, rice also, cassava also, but your imputation give maize declining, this is not coherence. Maybe what happened with this? That could be true, but you know the data better. Maybe because of the problems with the insect eating the maize, could be. But otherwise, these imputed figures should be incoherent with this one. So that's why when you are preparing the data for imputation, this should be some kind of a model, yeah, model of coherency. Another example, poverty theme. The same as poverty, maybe you have missing value on the poverty rate, the malnutrition, yeah, and then IMR, infant mortality. Those are related, yeah, should show some coherency among them. And you want to input this maybe you need some other auxiliary variables which have some kind of logical relation, yeah, some coherency. For example, the SDI, Human Development Index, should say something about poverty. And then the GDP growth, GDP per capita, agricultural production maybe, and manufacturing production for the urban, this is for the rural. Literacy rate related to the poverty, yeah. If you have a lot of poor people, maybe literacy rate will be lower. So this variable should be able to help you make the more plausible imputation. So this is what you mean by when you are asking to prepare your data. If you have this kind of data, and then you can do the exercise on while following us, and then see whether we get strange results or not. Yeah. And then again, I would like to mention, of course, this is good if you're talking about one country, yeah, because you have the same, what you call it, infrastructure in one country, maybe the same climate and the same policy of the government, yeah. So that kind of factor has been controlled here. If you are talking about country estimate, yeah. So the only thing is just to make sure that you have this kind of expected coherency, okay? But at the ASEAN level, we have many countries already, which maybe clearly have different infrastructure, different policy, etc. But there is some possibility still. If you are talking about some variables like poverty, poverty may still have something to do with the Human Development Index, GDP per capita, yeah, literacy, for example, and the presence of different countries here hopefully can still control the variability, yeah, among countries. But this is what I mean. Of course, like Singapore, all the indicators here are performing well. And then for the less developed country, is performing less. But we still can use Singapore because the algorithm will take care, yeah, this range of numbers, yeah. If you are within this range, and then the poverty normally within this range, yeah. And if the other indicators are within this range, the poverty normally within this range. So that kind of thinking, maybe we still, yeah, I believe still makes sense to impute the country data at the ASEAN level, but for use in ASEAN analysis only, ASEAN publication. Even we are not showing your figures, yeah. And if you are interested and want to do more to further develop the result of our imputation, this is very, very recommended. This is better. And you use that and then try to use your professional experience, your judgment, you're looking at the other data, and then you can say, okay, this is fine, but this is not fine, yeah. And then we can do some improvement. Okay, is there any other question?
Yeah, there is a request, Pak.
Yes, please.
To share the script for UK guest exercise that you just present.
Oh yeah, yeah. That I have not sent you. I will check. Yeah, I will share this to member states. I will send Hanik. Yeah.
Yes, Pak.
Yeah. And I will make sure that all the scripts with you, but most of them I think have been sent. I've been in the Dropbox. Eh?
Also the mice illustration, Pak.
Okay.
Yeah.
Yes. Maybe I will need to refine this a little bit because this is done very quickly this morning. Okay. I don't prepare quiz for this afternoon, but maybe I will give you tomorrow morning, yeah, before we start. Anything else we would like to discuss? Check this one. Okay, I think that's all for the day. Anik, I give the floor to you back.
Thank you very much, Pak Agus. And yeah, actually, this is the end of today's sessions. Don't forget, we have a task from Mr. Agus to prepare the country data that we will use for exercise. And we still have one more day tomorrow. And we will see you again tomorrow morning at 8:30 Jakarta time. And thank you and see you again tomorrow.
Thank you. See you tomorrow. Yeah, Mr.